Welcome everyone. Today we are looking at organic chemistry, and in this presentation this is going to be our first lesson looking at what we call organic chemistry. Okay, and in this session we are going to basically understand what organic chemistry is, what compounds do we look at in organic chemistry, and also we'll see why actually organic chemistry is very important, and we shall look at the unique features of these compounds that we call organic compounds, and specifically we shall be looking at carbon and see why carbon is quite unique, and that it actually combines with a number of different compounds or molecules or groups of atoms that form the basis of what we call organic chemistry. So organic chemistry is basically a branch of chemistry that deals with the study of what we call organic compounds. So we look at the structure, the chemical characteristics of all these organic compounds, and how they are actually prepared and how we actually use them. So throughout this topic, we shall be looking at the different categories of organic compounds, how they look like, that is their structure, molecular structure, and also structural formula, for example. We'll look at that. So we'll also look at their chemical reactions, and then we also look at the physical characteristics and how we prepare these compounds in the lab. And finally, we look at how they are used in science or in application, or even what are the things that we have at home that are made from these organic compounds. Okay, so what is the unique thing about these organic compounds? They have carbon. Okay, basically carbon is like a founding, if I can call it that, the founding atom for formation of these usually long chains of these what we term as hydrocarbons. Okay, you have a chain of carbon and hydrogen. Okay, so these actually form what you call the organic compounds. To bring this to what you already know, for example, you know proteins, right? The proteins contain carbon, hydrogen, and then also the nitro group, then another side chain, which can be a chain of hydrocarbons, or it can be another thing. So proteins, glucose, basically starch, and even lipids, they have the carbons and then the hydrogen. So we actually call them also organic compounds. Those are organic compounds. The proteins, the lipids, and also including the carbohydrates. Those are organic compounds. But of course, we have several organic compounds that we shall look at in this study. The unique thing always with these hydrocarbons, or these organic compounds, like I've said, they have carbon and then they have hydrogen. But they can also have other groups. Like I said, the nitro group, for example, that means that there's a nitrogen in there. We have phosphorus, we have halogens, we have sulfur. These are things that can still be attached to this long chain of hydrocarbons. Okay, so it's just like we are saying that the hydrocarbons, that is hydrogen and carbon, those chains can still also have other elements, okay, attached to them. And that's why we have mentioned phosphorus, sulfur, nitrogen, then oxygen, and other elements, as we shall see. Okay, so what you see here, perhaps you're asking yourself, what is that? This is actually one of the hydrocarbons, What I need you to pick from here is that these balls are actually representing carbon. Okay, so carbon is attached to other carbon atoms, and then also attached again to hydrogen atoms. These are basically the hydrogen atoms. So that is the picture I want you to get, that you have this long chain, which is like this, where you have carbon bonding with carbon and also bonding with hydrogen. Okay, but on top of that, we can still have other elements like we have just mentioned. Okay, so these are actually typically different compounds. They are not like the compounds that we are used to. So why do we form such kinds of compounds? The reasons align with the unique properties of carbon. Okay, carbon has the ability to form long chains because of the covalent bonds that are formed between carbon atoms or between carbon and other elements, for example, hydrogen. Okay, so that is what actually makes. This is another representation that we can. So you can have a continuation of this side and also the other side. A long chain, that's what we are referring to. You can see the carbon, okay, and then the hydrogen, right? So these bonds here, these are covalent bonds. That means that the electrons are being shared, okay? So apart from forming these long chains, they also form what you call rings. What you saw earlier on here, these are rings, carbon rings, right? Those are rings. So carbon also has that unique property of forming these rings that can also go on branching at different carbon atoms. Okay, so they can be extremely long with hundreds and thousands of carbon atoms. And then we move to another point which relates to what we call hybridization. So this is basically to say that carbon forms bonds with different atoms, but the way in which these atoms can be arranged in a compound can be different. So you have the same compound, that is to say, it has the same number of atoms, okay, the atoms of different elements, but the way these atoms are arranged can be different. So it's like you can have one compound like this, but it is arranged in different ways, and therefore you have different varieties of the same compound because of the arrangement. Okay, so that is the points that we are referring to here as hybrids. Hybrids, you have something here, and then from it you get other varieties, and these varieties are coming up because of the way the atoms are arranged or attached to the different carbon atoms. Okay, so that's why we have the way in which they appear, the geometric appearance, and the attachment of the functional groups are the ones that make them different. We shall see what functional groups are later on. Actually, here. So the functional groups are the groups of atoms, or even could be basically a group of atoms that give a particular organic compound its characteristics. Okay, it's the one that actually takes part in the chemical reactions of that organic compound. So it is the one, if I'm to refer to it as a human, it's the brain. Okay, it's the brain. The brain controls everything that happens on a human body, right? So the functional group, the nature of the functional group is the one that will determine the chemical characteristics of the organic compound. Okay, so the other part of the organic compound, does not actively participate in the chemical reactions. Okay, but this, of course, is the one that gives the functional group is that gives the characteristics and the reactivity. So when you have a long chain of carbon or hydrocarbon, you will need to look for the functional group. So if you say the functional group is the hydroxyl ion, the hydroxyl there is the one that will participate in the reaction and then forming the products. Okay, so there are very many functional groups, and these are not the only functional groups. So you have the hydroxyl, you have the carboxyl, you have the amines. Okay, so we have different organic compounds named according to their functional groups. So if you hear the alcohols, their functional groups are the hydroxyl, and then the carboxylic acids, they have the carboxyl group, okay, that forms their functional group, and then the amines that I also talked about earlier on, they are formed in what you call the amines. The phenylamine, these are, if you can hear the name, it is having that element there. Okay, hydroxyl. Okay, so you can see this here, the functional group. This here is the functional group. This here is the functional group. Okay, it's the functional group. So I guess you know what a functional group is. Now we move to what we call fast pass. Okay. So now we move to what we call the homologous series. So like we said, we have very many organic compounds, and we have just said that these organic compounds can actually be differentiated by their functional groups. But you can still have under the same line of organic compounds with the same functional groups, there are other elements in there. This is basically, for example, to say that we have very many types of amines, we have very many types of alcohols, we have very many types of carboxylic acids, right? So how do we differentiate them? There is always that unit here, the CH unit, that makes the difference. Okay, ethanol from propanol, for example, or methanol from ethanol. What's the difference? You realize that it's actually the CH group that makes a difference. So that means that all the, whether it is methanol, whether it is the ethanol, they belong to the same homologous series. Okay, and these usually have the same kind of general formula. And that's why they only differ with the CH group, or what you're calling the CH unit here. Okay, and because of the increasing, because this goes on increasing with the different compounds with the same functional group, right? So that means that there are some properties which are also going to be affected by the length of this chain. So issues to do with the melting point and the boiling points are actually going to be different for different members in the same homologous series. Okay, so like I started with, I said that organic chemistry looks at what you call the chemistry of hydrocarbon compounds that contain carbon and hydrogen. At this level, we are going to look at three major classes of these hydrocarbons. Okay, we are going to look at three major classes of hydrocarbons: the alkanes, and the first ones, the second ones are the alkenes, and then the third ones are the alkynes. Okay, so we are going to, we shall look at all these. For now, let's just know that the alkanes are those those hydrocarbons that are actually saturated. What we mean with the one saturated hydrocarbons is that they have only one, they have single carbon to carbon bonds. Okay, so the connection between carbon, for example, you see that with methane, this is the first member of the alkanes is called methane, right? So we are saying that you have one carbon and then four hydrogen atoms in methane. Okay. What we are saying with alkanes is that there are no double bonds. They have these only single bonds between carbon to carbon. So for one molecule of these, you'll have CH. Each of these is hydrogen, 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 and hydrogen. And this hydrogen can be connected to another molecule like that. But this ethane, for example, is what can bring out what I want to explain to you. That between carbon and the carbon, we are looking at this, remember, we have two carbon atoms. So between the carbon and another carbon, there is only one bond. And then the rest hydrogen, and that's why we actually have 6 hydrogen. We have 1, 2, 3, 4, 5, 6. So this is a single bond. That is what happens with alkanes. And then when we come to the alkenes, we have at least one double bond. Remember, the word is at least. You can have more double bonds within the same compound, but at least there should be a double bond. And this can be illustrated by this. Remember, carbon can bond to can form 4 covalent bonds. Okay, that is one rule that you have to. For each carbon atom has to combine with at least 4. Okay, it has to have at least 4 bonds. So with alkenes, we have the double bond between carbon and carbon. So if this one has, for this alone, there have to be at least 2 for it, for this one to have 4 bonds. 1, 2, 3, 4. So this one also has to get 2 more for it also to have 4 bonds. Okay, so if you count 1, 2, you have 2. How many? 1, 2, 3, 4. So H2. Okay, so that's what we have in. Okay, even when we write for this, there should be a double bond between the carbon and the carbon. Okay, so those are alkenes. All alkenes have a double bond, and that makes them more reactive compared to the alkanes. Okay, and then we'll come to the alkynes. For them, there should be a triple bond between carbon and carbon. So 1, 2, 3. Right? So that means that for this one to be complete, it only needs 1. For this one to be complete, only needs 1. So you have CH, these are 2, and the hydrogen are how many? They are also 2. So that's what we have with that. Okay, so those are the 3 categories of hydrocarbons that we shall look at. Compounds that contain hydrogen and carbon. Okay, and then we have looked at the bonds that make them different. For alkanes, single bond. For alkenes, you have double bond. For alkynes, you have 3 bonds, a triple bond between carbon and carbon. The other thing that you also notice with the hydrocarbons, like we said, that you have, for example, the alkanes. Within the alkanes, you will have methane, you will have ethane, right? Methane here, you have ethane, you have propane, you have butane, you have pentane, right? Where do they get their names? The naming of compounds in chemistry is called that nomenclature. How we name compounds is nomenclature. In organic chemistry, especially naming the organic compounds, we are interested in the number of carbon atoms that form up that compound. And then, even after knowing the number, then we also look at the position of the functional group. So the number and the functional group are very important in telling us about the compound. So here, what we can highlight as of now is the number of the carbon atoms. If you have one carbon atom like here, you will have this Me. Okay, METH, but both this is different. So for example, if you have, let me use the example of methane. So methane, let me write it here. That is methane, right? This part here is what tells us that this is an alkane. So when we write methyl, right, this here is what tells us that it is an alkene. If you write, if you write this, for this is an alkyne, right? The reason as to why we have actually started with this is basically to illustrate the point to do with the triple bond that have to be there. Okay, so you basically need to have two carbon atoms. Okay, so that is this ending part, which we call the suffix, tell us about the functional group at least for now, and then this what we call the prefix. So but, pent means 5, but means 4, pro means 3, this means 2, this means 1. Okay, that is the number of the carbon atoms in that compound. That's what we have there illustrated. Okay, now the second point, which I said that the length, which is determined by the number of carbon atoms there, but also the position of the functional group, or the presence of the functional group. And we need to indicate where that functional group is. Okay, but that is not something that we can look at this level. So isomers, remember earlier on we said that you can have the same compound, with the same number of atoms, that is whether it is hydrogen or whether it is carbon, but the way these atoms are actually arranged is different, yet everything is the same. Okay, so you can imagine it's just like me having this tie. Instead of having it here and then I tie it around my stomach, it still means that I have the tie, but the tie is placed in another position, right? So it's the same thing with what you call isomers. You have the same kind of molecular formula, okay? That is the same number of atoms that make up that organic compound, but where they are placed is what makes them different. So the way it looks is not the same. Okay, so that is what you call an isomer. The concept is called isomerism. Isomerism. I know, yes. Let me write it again. The concept is what you call isomerism. Okay, that's the concept there. Okay, you can edit that out and have this name clearly put there. Okay, I hope that is very, very clear. So the way the atoms are arranged can affect how that compound actually will react. Okay, if for example you have the functional group that is well positioned and exposed, then the reaction will be faster compared to if the functional group is hidden and the reaction can easily take place. So why are we interested in these hydrocarbons? There are a lot of things that we use at home, even at work, and these things are actually made up of hydrocarbons. The fuel that we actually use, whether it is in at home, whether it is in cars, this fuel can actually be made from these hydrocarbons. And for example, methane, which is the simplest hydrocarbon, is used as natural gas for heating, cooking, and electricity generation. Propane is also used as a fuel in cooking, heating, and also for different engines. Hexane is also useful as a solvent for extraction of edible oils from seeds and vegetables, and also have different uses actually at the industrial level. Okay, the plastics that we use, these are actually made as a result of polymerization that we shall look at later on. The plastics we use, for example, the basins, the cups, and some of the plates are made because of hydrocarbons. Okay, the polyethylene, the packaging, the containers, the plastic bags, all those are made from hydrocarbons. And then the candles that you use for your birthdays and things like that, they're made from hydrocarbons. Okay, and the dark wax can actually be used for a number of uses. Okay, and then some of the drugs that we actually take contain hydrocarbons, and these actually protect the drugs by maintaining issues to do with stability, solubility, and bioavailability. Okay, so that marks the end of this session where we have looked at hydrocarbons, the chemistry basically of organic compounds, where we say that carbon is basically like a framework for these organic compounds. So these organic compounds can often be of different varieties, but what basically differentiates them is the possession of a functional group, which we say is the group of atoms that determine the chemical characteristics of the compound. Their position in an organic compound can also influence the nature of chemical reactions that compound would be involved in. We said that carbon has some unique features, and one of the unique features is the ability to form long chains and forming bonds within itself. And these bonds can be single, triple, double bonds. Okay, and these are actually covalent bonds. And carbon, as an atom, actually requires to be filled with at least can have at least 4 bonds. Okay, these bonds can be, some of them can be between carbon and carbon, some of them can be between carbon and hydrogen, or even other groups. Okay, and we also say that these hydrocarbons exhibit what we call isomerism, which is a concept related to the arrangement of the atoms in a compound. You can have a compound of the same molecular formula but different structural formula. This is to say that if they have the same number of atoms, okay, whether it is hydrogen, whether it is carbon, it's the same number, but the way they are arranged, the way they are bonded will be different. And structurally, if you draw that structure, you will have something different coming from the same thing. Thank you for listening.